Volume, solids with known cross-sections. Objective, find the volume of a solid with known cross-sections. Before we get started with our discussion, I'd like to make a point. Prior to this, we've been working with the disk method and the washer method, and we use those methods to find the volume of a solid of revolution, meaning we took a region in the xy plane, and we took that region and we revolved it about a particular axis of revolution, whether the axis was horizontal or vertical, and we obtained a solid of revolution. In other words, we began with a region in the xy plane, we took that region, that two-dimensional region, and revolved it about a particular axis of revolution, a line, and that gave us a solid of revolution. So we obtained a solid by revolution. Now this problem is different. We have a region in the xy plane to begin with, just like we had before, but we're not going to revolve it about a particular axis of revolution. Instead of doing a revolution about a particular axis of revolution, we're going to do the following. Our region in the xy plane will become a base upon which we will build our solid. So you can think of this as the floor of a building. So our region in the xy plane becomes like the floor of a building, and then on this floor plan we're going to build up to get our three-dimensional solid. So build up towards the sky to get our three-dimensional solid. And there's going to be a certain consistency in how our building is constructed. For example, in this particular problem that we'll look at in this lesson, cross-sections perpendicular to the x-axis will be squares. So in this particular example, the region that's going to form the floor of our solid, or the base of our solid, is the region in the xy plane bounded by the graph of x squared plus y squared is equal to 4, which is a circle centered at the origin with a radius of 2 units. And the consistency we'll have in this solid is that cross-sections perpendicular to the x-axis are going to be squares. So what we see here are vertical line segments that are perpendicular to the x-axis. All I've done here is I'm taking a look at the same base of our region from a different perspective. And this is the consistency that I was talking about earlier. Cross-sections perpendicular to the x-axis will be squares. What do we mean by a cross-section? So you can, for example, imagine that our solid is a cake. And if you take a knife and you slice your cake so that your knife is perpendicular to the x-axis. If you slice it once, you can separate your cake into 2 pieces, and if you look at it from the side, you will see a cross-section that is a square. Here we see 4 such squares, starting with the smallest one on the right side, which is black, and then the next one, which is blue, and then the last 2 are similar colors, a darker violet and a lighter violet. But each one of them are squares. That's what they have in common. So how do we find the volume of this solid of revolution? Let's see if we can first visualize what the solid of revolution would look like, and then we'll talk about how we can think about finding its volume. So what I'd like to do now is run through a series of slides so you can visualize our solid being formed. So right now what you see is one particular cross-section. It is in the shape of a square. It is taken at an x value that's close to -2. And of course, depending on where the cross-section is taken, either you'll have a smaller square like the one that you see, or a larger square like the one that we'll see soon. So for example, if you take a cross-section at x is equal to 0, then at that value of x, you'll have the largest possible cross-section. It'll be a square, and the length of each side would be 2 minus negative 2 or 4. So the length of each side of the square that I just drew in red would be 4 units. So we can easily find the area of that square. It would be 4 times 4 or 16 square units. And we're going to have to use that to find an approximation of the volume of this solid of revolution, but we'll get to that in a moment. So observe how these squares are going to form our solid of revolution. Now let's look at the same sequence, but with the outline of our solid shown. So this is the solid that we get. And I've shown 4 cross-sections within this solid. And our problem is to approximate, actually we want to find the exact volume of this solid that we just obtained, not by revolution, but by building on a base with known cross-sections that are perpendicular to the x-axis, squares in this particular problem, but it could be another shape like semicircles or rectangles, for example. But in this problem, we have squares. How do we find the exact volume? There's no way for us to do it using a formula from geometry, so we're going to go through the same process that we went through to develop the disk method. We'll begin with an approximation. We'll think about how we can make our approximation better, take that idea to the extreme, and we will have the limit of a Riemann sum, which will give us a definite integral. Before we get into those details, let's visualize our solid furthermore just by looking at a few more slides so you can see it from different perspectives. So now we want to find the volume of this solid. How can we do that? As we mentioned earlier, there's no formula from geometry that will give us the exact volume, but we can use a formula from geometry multiple times to come up with an approximation for the volume of this solid. And what formula are we going to use? How to find the volume of a rectangular prism. So how do you find the volume of a rectangular prism? Many students will tell right away that to find the volume of a rectangular prism, you need to know the length, the width, and the height. And you do length times width times height. But make this observation. If you do length times width, you're finding the area of this surface. And in our problem, that is going to be the area of a particular cross-section in our solid. So how do you find the volume of a rectangular prism? Length times width times height, but length times width is going to give you the area of one surface. So we're going to write A for the area of one surface, and then multiply that by the height. And that's going to give us the volume. So to approximate the volume of this solid, what we're going to do is we're going to find the volumes of several rectangular prisms, and then we'll add these volumes together, and that'll give us an approximation for the volume of the solid. So how do we go about this in a very precise and methodical way? We'll begin by thinking about the base of our solid. It is a circle centered at the origin with a radius of 2 units. And we're taking cross-sections that are perpendicular to the x-axis, and each cross-section is a square. So we're going to start at the left end of our circular base at x is equal to negative 2, and go all the way to the right end of our circular base at x is equal to positive 2. And what we have to do is we have to divide our interval from -2 to +2 into a number of subintervals. That is called forming a partition. So you have your choice of how you'd like to form your partition. For example, you can form your partition with 8 subintervals. And if you'd like to make it a regular partition where all of the subintervals have the same width, the width of each subinterval would be, you take the width of the interval from -2 to +2. 2 minus -2 is 4. And if you divide 4 by 8, you get 1/2 for the width of each subinterval. So if you do that, then you're going to have a total of 9 partition points. And I've listed all of them. X naught would be -2. X sub 1 would be -1.5, x sub 2 would be -1, x sub 3 would be -0.5, x sub 4 would be 0, all the way to x sub 8, which is going to be 2. And it is possible for you to find the width of each subinterval. The width of each subinterval can be found simply by subtracting the x-coordinates of consecutive partition points. So for example, the width of the first subinterval can be found by taking x sub 1 and subtracting x naught from it. -1.5 minus -2 is 0.5. How does that help with being methodical? Because now on each subinterval, in our particular partition that I'm using as an example, we have 8 subintervals. On each subinterval, I'm going to choose an x value. For example, for our first subinterval, I can choose an x value somewhere between -2 and -1.5. And maybe I just want to be consistent and choose all the right endpoints of each of my subintervals. So if that's the case, my first point that I choose, which I will call a sample point, from the first subinterval would be -1.5. The sample point from the second subinterval would be -1 at the right endpoint of the second subinterval. The sample point from the third subinterval will be -0.5, and the sample point from the last subinterval would be at x is equal to 2. And at each of these sample points, I'm going to construct my perpendicular cross-section to my solid, which will be a square. So for example, on my fourth subinterval, I will choose the right endpoint of that subinterval, which is x is equal to 0, and I will construct my perpendicular cross-section to the x-axis, which will be a square. And that's what I'll have. So that's the cross-section that is perpendicular to the x-axis, and in this problem, our cross-sections are all squares. So the width of my fourth subinterval is 1/2. So now that's going to be the height of my rectangular prism. And that's going to be delta x sub 4, which is going to be x sub 4 minus x sub 3. And that is the difference of 2 consecutive partition points from my partition. And because the height is given by a difference in x coordinates, it is notated as delta x with the subscript 4 for my fourth subinterval. The height of each rectangular prism is given by a change in x. And this is something important for you to understand when you will be thinking later about particular problems and whether you should integrate with respect to x or with respect to y. So keep that in mind. So how are we going to find the volume of this one particular rectangular prism? We'll use our formula. The volume is equal to the area of the base multiplied by the height. And of course, the area of the base is going to be the area of our cross-section that is perpendicular to the x-axis. So how can we find the area of each square that's perpendicular to the x-axis? And of course, we can see very clearly that depending on where the square is constructed, it will either have a large area or a smaller amount of area, like the one for the black square that we're looking at towards the right end of our solid. So the area depends on where the cross-section is taken. And where the cross-section is taken will be designated by a particular x value. So we need a function of x that will give us the area of each square cross-section. How will we get that? To answer that question, we can go back to our base that we're building from. And you can see that we have these vertical line segments at different x values, and I'm going to highlight just a couple or maybe 3 of them. And you can see that they're at different places, and where each vertical line segment is given by an x value. So for example, it looks like here the x value might be something like maybe 1/4 for this particular vertical line segment, and this one it looks to be a little bit more than 1, and this one it looks to be somewhere between -1 and -2. So the x value tells us where the vertical line segment is. Now we need a function of x that will tell us the length of a vertical line segment, but we know how to do that because we've learned this in a previous lesson. To find the length of a vertical line segment, you subtract the y coordinates of the top and the bottom endpoints in that order, top minus bottom. So what is going to be the y coordinate of a top endpoint of each vertical line segment? What is going to be the y coordinate of the bottom endpoint of each vertical line segment? Well, let's look at that. So the equation for the base of our solid is x squared plus y squared is equal to 4. It's a circle centered at the origin with a radius of 2 units. And we're going to solve this equation for y. We begin by subtracting x squared from both sides of the equation. And then we take the positive and the negative square root to find y. Now, here's what you need to understand. This circle, it has a top part, the top half of the circle, I'm going to highlight that, it's in quadrants 1 and 2. And in these 2 quadrants, the y coordinates are positive. So if you have any point on the circle in quadrant 1 or 2, you're going to take the positive square root. And if you have any point on the circle that's in either quadrants 3 or 4, where y coordinates are negative, you're going to take the negative square root. So if you have a point on the top half of the circle, what will be its coordinates? The x coordinate is variable between -2 and +2, so we have x for the x coordinate, and the y coordinate will be the positive square root of 4 minus x squared. If you have a point on the bottom half of the circle in quadrants 3 and 4, what coordinates will we have? Again, the x coordinate is variable from -2 to +2. The y coordinate would be the negative square root of 4 minus x squared. So now we're ready to write a function of x that will give us the length of an arbitrary vertical line segment between the top and the bottom halves of our circle. And that's going to be given by r of x is equal to, subtract the y coordinates of the top and the bottom endpoints, so we'll have the square root of 4 minus x squared minus the negative square root of 4 minus x squared. And when you simplify this, what do you get? You're going to get 2 times the square root of 4 minus x squared, because when you subtract negative square root of 4 minus x squared, that's the same as adding, and you add the 2 like radical expressions. So we now have a function of x that will give us the length of an arbitrary vertical line segment between the top and the bottom halves of our circle. And we can use that to write a function of x that will give us the area of each cross-section. So we're going to have a function of x that'll give us the area of each cross-section. So we're going to get a function of x that will give us the area of each cross-section. And then once we have that, we need to multiply by the height, which is going to be given by delta x sub I. And this is going to be called delta v sub I. All that means is this is the volume of the ith rectangular prism that we have constructed on the ith subinterval of our partition. And we will have a number of these in the partition that I've mentioned in this video. We're going to have 8 of these. And we'll add the volumes of these 8 rectangular prisms together. That'll be a Riemann sum, and that will give us an approximation for the volume of our solid. That's a Riemann sum. We have a sum of products, and each product is formed by taking the area of each cross-section and multiplying by the height. And we have several of these. In my example, n would be 8 because I'm using 8 subintervals. But of course, you can get a better approximation by increasing the number of subintervals that you have and making sure that the width of the largest subinterval approaches 0. So that's how you get an approximation for the volume of the solid. How do you make it better? Increase the number of subintervals while also making sure that the width of the largest subinterval is getting smaller and smaller and smaller. So if I wanted to do that, for example, I could have a partition with 16 subintervals of equal widths. The width of each subinterval would now be 1/4 of a unit, and I can have 16 rectangular prisms and find the volumes of the 16 rectangular prisms and add them together, and that would be a better approximation than just using 8. So if we take this idea to the extreme, we can take the limit of this Riemann sum as the norm of the partition approaches 0, which implies that the number of subintervals will be approaching infinity. And by the definition of a definite integral, what is a definite integral? It's precisely the limit of a Riemann sum as the norm of the partition approaches 0. So this is going to give us a definite integral. The limits of integration would be from the least x value of your partition points to the greatest x value of your partition points. The integrand would be a of x, signifying the area of each cross-section. And we're integrating with respect to x because the height of each rectangular prism is found by subtracting 2 consecutive x values from our partition points. So let's go back to our slide from earlier and see if we can apply the integration formula that we came up with to find the exact volume of our solid. So the definite integral, by definition, will give the exact volume of our solid. And let's see if we can find the exact volume of the solid in this particular problem by applying that definite integral. So here's our definite integral that we came up with. And the integrand is a function of x that would give us the area of each cross-section that is perpendicular to the x-axis. We're integrating with respect to x, and the limits of integration are x coordinates, the least and the greatest x coordinates from our partition points. So our partition points start at x is equal to -2, and they end at x is equal to +2. So the limits of integration that we have in this problem are from x is equal to -2 to x is equal to +2. What about the integrand? We know why we're integrating with respect to x, again, because if you go back to the way our rectangular prisms were constructed, the height of each rectangular prism is given by a difference in 2 consecutive x coordinates from our partition points. Now for the integrand, we need a function of x. Everything has to be consistent. Remember that. If you're integrating with respect to x, the limits of integration are x values, and your integrand is a function of x. Our integrand must give us the area of each square cross-section that is perpendicular to the x-axis. And how do you find the area of a square? You take the length of one side and you square it. So that's what we're going to do, because now we have a function of x that gives us the length of one side of our square. Look at me as I trace the length of one side of our square, which will be the length of a vertical line segment along our base. From the top half of the circle drawn to the bottom half of the circle. And earlier we found a function of x that would give us the length of this vertical line segment, which would in fact be the length of one side of our square cross-section that is perpendicular to the x-axis. So how do you use that length to find the area of your square cross-section? How do you find the area of a square if you know the length of one side? You square that length. So we know the length, we know a function of x that will give us the length of an arbitrary vertical line segment in our region. And we're going to take that, and that is 2 times the square root of 4 minus x squared, and then we're going to square that. So that's what we have. And of course you can simplify the integrand. You will have volume is equal to the definite integral from -2 to +2. And 2 squared is 4, and if you square the square root of 4 minus x squared, you're going to get 4 minus x squared dx. And of course you can further simplify by either factoring out the 4 or distributing it, whatever you want to do. But that would be the definite integral that would give the exact volume of our solid. So in this lesson we looked at how to find the volume of a solid with known cross-sections. And for the example that we looked at, we used this particular integration formula. Why? Because we had cross-sections that were perpendicular to the x-axis. Now if you have a different example where you have cross-sections that are perpendicular to the y-axis, you would integrate with respect to y. And in our particular example, the cross-sections perpendicular to the x-axis were squares, but you could have cross-sections that are semicircles, maybe rectangles, etc. And whatever the shape of each cross-section is, the integrand will give you the area of a particular cross-section where x tells you where the cross-section is taken. This was the particular example that we looked at, where the region that we have for the base of our solid is a circle centered at the origin with a radius of 2 units, and cross-sections perpendicular to the x-axis were squares.